All right, let's dive right into this explainer. Today, we're unpacking the absolute mathematical engine that powers modern machine learning, singular value decomposition, or SVD, and matrix factorization. We're going to be pulling heavily from chapters 7 and 8, specifically pages 341 through 434 of Charusi Agarwal's definitive text on linear algebra and optimization. If you work with data, you already know the deal, right? Raw data sets are messy, they're massive, and quite frankly, overwhelmingly noisy. But hidden inside all that chaos are clean underlying patterns. So today we're going to look at the exact mathematical mechanisms we use to pull those patterns out.
Now, look at this quote on the screen. Calling SVD a high point of linear algebra really isn't just academic hyperbole from our source textbook. It's a genuine recognition that SVD is essentially the ultimate mathematical tool for extracting signal from massive, noisy datasets. It's the bridge, really, between pure mathematical theory and the pragmatic, often messy reality of machine learning algorithms.
To demystify all of this, here is our roadmap. We'll start with the magic of SVD, move to the linear algebra view, then the optimization view. After that, we'll generalize matrix factorization, and finally, look at real-world ML applications.
Jumping into Section 1, the magic of SVD, decomposing complexity.
So, fundamentally, what is SVD actually doing? Well, it takes a complex, high-dimensional data matrix and it just breaks it down. Think of it like factoring the number 6 into 2 times 3, but scaled way up for massive data matrices. Specifically, it takes an arbitrary matrix and decomposes it into 3 simpler ones. 2 of these act as rotation or reflection transformations, and that middle one acts as a non-negative scaling matrix. By factoring the matrix into these simpler components, we're essentially rewriting a complex linear transformation as a sequence of highly predictable, easy-to-compute steps. It's pretty brilliant.
Check out the visual breakdown here. We start with our main matrix, D, and we factor it down into a U matrix, a sigma scaling matrix, and a V transpose matrix. Notice how this specific factorization completely avoids irrational numbers? It gives us this incredibly clean mathematical representation of the original data. It proves that right beneath seemingly random arrays of numbers, there is an elegant, structured factorization just waiting to be discovered. Moving right along to Section 2, the linear algebra view, focusing on exact decomposition. Now, chapters 7 and 8 heavily emphasize this crucial duality, and it's really the core of this whole explainer. On one side, you've got the linear algebra perspective. This view is all about guarantees, right? It ensures an exact, perfect mathematical breakdown of the matrix, completely focused on pure vector spaces. But then, on the other side, we have the optimization perspective, and this is really where machine learning lives. Out here in the wild, we don't care quite as much about perfect, exact reconstruction. Instead, we want the absolute best, most efficient approximation of the data so we can compress it and find those hidden low-rank structures.
But sticking with the linear algebra side for just a second, theoretically, SVD is perfect. You know, standard diagonalization? Great concept, but it only works for nice, neat, square, symmetric matrices. SVD, on the other hand, is guaranteed to exist for any arbitrary matrix. Literally, no matter its size or shape. It basically takes the whole concept of diagonalization and generalizes it for the entire mathematical universe. The singular vectors it produces align perfectly with the eigenvectors of the data's scatter matrices. Ultimately, SVD is like a master key that unlocks all 4 fundamental geometric subspaces of our data.
Which brings us to Section 3, the optimization view, where we hunt for the best approximations.
Take a look at the math playing out here with this residual matrix calculation. If we truncate the SVD, meaning we only keep the largest, most important singular values and toss the rest, we can actually approximate a matrix remarkably well using just a tiny fraction of the data. That residual? That's just what's left over after we strip away the dominant patterns, and in machine learning, that residual is usually just noise. By isolating the top singular vectors, we keep the signal and we throw away the noise.
And this optimization perspective proves a pretty monumental concept in data science. When there are 0 constraints, SVD gives us the absolute best low-rank approximation possible. Think about it. If you want to compress a dataset into a smaller matrix and you want the mathematically guaranteed lowest possible error, unconstrained SVD is your gold standard. For sure, it's literally the theoretical ceiling for how well data can be compressed linearly.
All right, Section 4, generalizing matrix factorization by adding real-world constraints.
Because, let's face it, as incredibly powerful as SVD is, once you introduce real-world constraints, the rules of the game change entirely. A classic example is requiring non-negative numbers.
If you're analyzing text documents, you obviously can't have a negative word count. As soon as you impose a constraint like non-negativity, the space you're working in is no longer a standard vector space, meaning the elegant rules of pure linear algebra just go out the window. We literally have to leave exact algebraic decomposition behind and shift into the broader, way messier world of general matrix factorization. We start relying on non-convex optimization and algorithms like gradient descent to hunt down our best approximations.
Finally, Section 5, Machine Learning Applications. Let's see SVD out in the real world. This breakdown perfectly summarizes why all this dense math actually matters to us. SVD is the direct engine driving principal component analysis, PCA, shrinking massive datasets while keeping the variance intact. Then generalized matrix factorization, that's the exact math working behind the scenes in recommender systems. You know, when a streaming app predicts exactly what movie you want to watch next based on a massive, super sparse matrix of user ratings, and non-negative matrix factorization is the absolute standard for text and graph engineering, letting algorithms cluster documents in ways that are actually interpretable to us humans because the parts are strictly additive.
All of this leaves us with a pretty fascinating thought. If every seemingly infinite, overwhelmingly complex data set we generate every single day can be elegantly factored down into a smaller, low-rank approximation, whether that's through pure SVD or constrained gradient descent, how much of our digital reality is actual, unique signal, and how much is just beautifully compressed mathematical noise? It's a profound realization about the true nature of information itself, and honestly a perfect place to wrap up our explainer on this fundamental ML concept. Keep learning, keep optimizing, and I'll catch you in the next one.